Next example, solve the equations 3x plus y plus 2z is equal to 3, 2x minus 3y minus z is equal to minus 3, x plus 2y plus z is equal to 4 by Gauss-Jordan elimination method or Gauss-Jordan method. Okay, the unknowns are x, y, z. In the place of x1, y, x1, x2, x3, the unknowns are x, y, z. Now reduce the system in the matrix form first. That is, write the coefficient matrix 3, 1, 2, then 2 minus 3 minus 1, 2, 1, 2, 1. X, y, z is equal to 3 minus 3 minus 4, and then consider the augmented matrix AB. So the augmented matrix is what? AB 3, 1, 2, 3, 1, 2, 1, 2 minus 3 minus 1, and 1, 2, 1, and the matrix of constant is 3 minus 3, 4. So combination of A and B is the augmented matrix AB. Now we have to solve this system by using Gauss-Jordan method. Means we have to reduce the system to reduce row echelon form. In the place of in the Gauss elimination method, we have to reduce the augmented matrix to echelon form or row echelon form. But in Gauss-Jordan method, we have to reduce this augmented matrix to reduce row echelon form. So we replace this one by 3 by 1. So interchange the first row and third row. So we have 1 at this place. Then reduce this 2 and 3 to 0. In order to reduce 2 and 3 to 0, the operations are R2 minus 2R1. That is multiply by minus 2, add in this. And then multiply by minus 3 in this to this one and add this. So R3 minus 3R1. So these are operations. We have 0 at this place, and these elements are also changed because minus 4 minus 3 become minus 7. Then minus 2 minus 1 becomes minus 3. Then minus 8 minus 3 become minus 11. Then multiply by minus 3. So minus 3 plus 3, 0. Then minus 6 plus 1 minus 5. Then minus 3 plus 2 minus 1. And minus 12 plus 3 minus 9. Then we have to reduce this minus 7 to 1. So in order to reduce this minus 7 to 1, either use the row below, situated below this row, or the last operation is what? Minus 1 by 7 R2. That is, multiply this second row by minus 1 by 7. So we have 1 at this place. We have some fractions, but it is not possible to avoid these fractions 3 by 7, 11 by 7, because in order to reduce this minus 7 to 1, we have to apply the transformation minus 1 by 7 R2. So we have this, multiply by minus 1 by 7 to this row. We have 1 at this place. Then reduce this minus 5 to 0. In order to reduce minus 5 to 0, operation is what? Transformation is what? R3 plus 5R1. So by using this one, reduce this minus 5 to 0. So R3 plus 5R2. So multiply by 5 and add in this row. So the first row, second row as it is, the change in the third row. So we have 0 at this place. And then my 5 into 3 by 7 minus 1 is 8 by 7. And then 5 into 11 by 7 minus 9 is minus 8 by 7. Then we have to reduce this 8 by 7. Then we have to reduce this minus to 0. This plus 2 to 0. Because we have to reduce the matrix, augmented matrix AB to reduce row echelon form. So what is the reduced row echelon form? The one more additional condition in the echelon form. What is that? That is the columns containing leading one has all 0 elements except that one. So this column contains leading one. This column contains leading one. Now we have to reduce this 2 also to 0 because the second column contains leading one. So in order to reduce this minus 2 to 0, operation is R1 minus 2 R2. By using this one, we reduce the element below 0, the element below 1 to 0, the element above 1 to 0. So R1 minus 2 R2. So we have 0 at this place, but minus 2 into 0 is 0. So plus 1 as it is. But this minus 2 plus 2 becomes 0. Then minus 2 into 3 by 7 minus 6 by 7 plus 1 is 3 by 7. 1 by 7, and then minus 2 into this minus 11 minus 22 by 7 plus 4 becomes 6 by 7. Then we have to reduce this 8 by 7 to 1. So the operation is 7 by 8 R3. 7 by 8 R3. Then we have 1 at this place, we have minus 1 at this place. Then we have to reduce these two elements to 0, because this third column also contains leading 1. So we have to reduce this 3 by 7 and 1 by 7 to 0. So operations are R1, that is this 1 by 7 lies in the first row. So R1 minus 1 by 7 R3, by using 1 reduce this to 0. And then R2 this is 3 by 7, for this 3 by 7 the operation is what? R2 minus 3 by 7 R3, minus 3 by 7 R3. So we have this matrix change is what? We have 1 0 at this place 0, and minus 1 by 7 into minus 1 become plus 1 by 7, plus 1 becomes 6 by 7. Okay, minus 1 by 7 into minus 1 become plus 1 by 7, plus 1 becomes 6 by 7. Minus 1 by 7 into minus 1 plus 1 by 7 plus 1 plus 1 plus 1 by 7 is, I think, 8 by 7. Yeah, right, 8 by 7. It is not 6 by 7. And then R2 minus 3 by 7 R3. So we have 0 at this place, 0 at this place, because minus 3 by 7 plus 3 by 7 0. And then minus 3 by 7 into minus 1 becomes plus 3 by 7 plus 11 by 7 is 14 by 7. 14 by 7 means 2. 14 by 7 means 2. And this 1 by 7 minus 1 by 7 into minus 1 become plus 1 by 7 plus 6 by 7. 1 by 7 plus 6 by 7. Okay. It is what? 1 by 7 plus 6 by 7 is 7 by 7. That is 1. This is correct. This is not 8 by 7. It is correct, that 6 by 7. So here is we have 1. Here we have 11 by 7 plus that 3 by 7 becomes 14 by 7, means we have 2 at this place. And then this is a reduced row echelon form. This matrix is now in a reduced row echelon form. And if we find the rank of A, this is the echelon form of the matrix A. This is the reduced row echelon form of the matrix A. Up to this, delete this row, delete last row. We have, this is the echelon form of the reduced row echelon form of the matrix A. And we observe the first row is non-zero, second row is non-zero, third row is non-zero. Okay, and therefore rank of A is 3. So here write rank of A is 3. And if you consider whole this matrix, this is a reduced row echelon form of the matrix AB, augmented matrix AB. And if you observe this matrix, this is reduced row echelon form of the matrix AB. So this row is non-zero, this row is non-zero, this row is non-zero. Therefore, rank of AB is also 3. And therefore, we denote that rank of A is equal to rank of AB. And therefore, the given system is consistent. So write that matter first, that the rank of A is 3, rank of AB is 3, rank of A is equal to rank of AB, and therefore the system is consistent and is equal to the number of variables. Rank of A is equal to rank of AB is equal to the number of variables, and therefore the system has obviously unique solution. And so how we can find the unique solution? Rewrite the equation from this matrix. So x, 1 into x plus 0 into y plus 0 into y, that is x is equal to 1. We have x is equal to 1. Then 0 into x plus 1 into y plus 0 into z means y is equal to 2. And lastly, 0, this into x plus this into y plus this into z means z is equal to minus 1. So we have the solution by Gauss-Jordan method or Gauss-Jordan elimination method. So next problem is also of the same type. Solve the equation by using Gauss-Jordan elimination method, Gauss-Jordan's method. So consider the augmented matrix, reduce the augmented matrix to reduced row echelon form, and then we have x is equal to 2, y is equal to minus 1, z is equal to 3. So solve the system. Next example again by Gauss-Jordan elimination method. We are given 4 equations and there are 3 unknowns. But don't change the method, that is form the augmented matrix. There are 4 equations and 3 unknowns. But we consider the matrix form and then consider the augmented matrix. So 3 2 minus 1, 5 3 2, then 3 1 3, and minus 6 minus 4 2, then 15 0 11 13 is the matrix, constant matrix. So this is the augmented matrix. So by reduce this matrix to echelon form. So in order to reduce this matrix to echelon form, first reduce this 3 to 1. So don't follow another procedure. Use this and your regular procedure. We have, this is the reduced row echelon form. Everyone has, this is the reduced row echelon form. The method may be different. These operations depends on you. These row transformations are depend on you. So, but follow the procedure, that is reduce this element to 1, then reduce the below element to 0, then reduce this element to 1, and then reduce the below and above element to 0, because we have to reduce the matrix to reduce to echelon form. Then reduce this element to 1, and then reduce the below and above elements to 0. So this is the procedure to obtain the reduced row echelon form. So we have, this is the reduced row echelon form. And if you observe the rank of A, that is, this is the echelon form, reduced row echelon form of the matrix of A. And we know that what is the rank of the matrix? Rank of the matrix is the number of non-zero rows in its reduced row echelon form, or number of non-zero rows in its echelon form. So this is the, this up to this, by deleting this last row, the remaining is what? The remaining is echelon form, reduced row echelon form of the matrix A. And if you observe the first row, non-zero, this is non-zero, this is non-zero, but the last row is 0 row, and therefore rank of A is 3. And now if you observe the whole matrix, whole form, this is the echelon form of the matrix, reduced row echelon form of the matrix AB. And if you observe this matrix, then also this is non-zero row, this is non-zero row, this is non-zero row, and the last row is 0 row. Therefore rank of AB is 3. So what we have, rank of A is equal to rank of AB is equal to 3, and therefore and is equal to number of variables. The number of variables in the given system are 3, and therefore the given system is consistent and has unique solution. And how we can obtain the solution? We rewrite the equation. So x is equal to -4, y is equal to 2, and z is equal to 7. So this is the Gauss-Jordan elimination method, or Gauss-Jordan method. So there are 2 methods to solve the system: Gauss-Jordan elimination method and Gauss elimination method. So solve the homogeneous system by any method. So this is the system. Write the system in matrix form. So 2 1 3, 1 2 0, and 0. The coefficient of x is 0 1 1. X y z is equal to 0 0 0. If you observe this system, this is the homogeneous system, because the matrix of constant is 0. So in this system, in the homogeneous system, either consider the augmented matrix A0, or consider the matrix A, the coefficient matrix A, right? A0, that is 1 2 0, then 2 1 3 0 1 1, and last column, right? Last column 0 0 0. So consider the augmented matrix A0, or just consider the matrix coefficient matrix A, and reduce the matrix to echelon form. So this is the echelon form, and then rewrite the equations. So we have sig z is equal to 0. Last equation is what? Sig z is equal to 0. The first equation is x plus 2y is equal to 0, then y plus z is equal to 0, and then sig z is equal to 0. So last equation, sig z is equal to 0, gives z is equal to 0, and then y is equal to 0. By back substitution, x is equal to 0 is the solution of this system. So the homogeneous system is always consistent. So no need to write the rank of A and rank of AB. Both are always same. So next example. This is the example: x, y, z, u. So there are 4 variables: x, y, u, x, y, z. So u, x, y, z. So in the first equation there is no variable u, so its coefficient is 0. Coefficient of x is 2, y is 2, z is 4. Then u coefficient is 1, X coefficient is 0, Y coefficient is -1, Z coefficient of is -2, 3, 1, 1, then -2, 1, 3, -2. And then this is the homogeneous system. So consider just matrix A and reduce the echelon to the echelon form, and then write X plus then U plus U minus Y minus 3Z is equal to 0 is the first equation. Then X plus Y plus 2Z is equal to 0, and last Z is equal to 0. So we have here we have the rank of, if you observe, the rank of A is 3, and rank of AB is also 3 in this problem. Rank of AB or rank of A0. So the rank of A and rank of AB are equal. The system is consistent, but it is strictly less than the number of variables. Number of variables are 4. So here we have 3 equations. We have number of variables. This rank of A is equal to rank of AB is equal to 3, is strictly less than number of variables, and therefore the system has infinitely many solutions. So if you observe these equations, so there are 3 equations and 4 unknowns. So we have to assign one unknown. Already we have Z is equal to 0. So assign either Y or X or U. So suppose Y is T, or take Y as a yes, or take Y as a R. What is T? T is any real number. So mention here that T belongs to R. T belongs to R, or T is any real number. So we assign Y is equal to T. When we assign the variable, if after rewriting the system, if we have the number of equations strictly less than the number of variables, then assign the variables. And how many we have to assign the variables? If you observe this, we have 3 equations and 4 unknowns. So the difference is 4 minus 3, that is 1. So we have to assign one unknown. So if we have 2 equations and if there are 4 variables, then the difference is 2. So assign 2 unknowns. So if I have one equation and if there are 4 variables, then the difference is 3, and therefore we assign 4 minus 1, that is 3 variables. So in this case, we have 3 equations and 4 unknowns. So difference is 1. So assign one unknown out of U, X, Y, Z. We assign one unknown. We already have Z is 0. So assign either X or Y or U. So here suppose Y is equal to T, and therefore this equation X plus Y plus 2Z is equal to 0 gives, substitute Z as 0 and Y as T. We have X is minus T, and then equation number 1 gives, this equation 1 gives U, then Y is minus Y 16 plus Y, and 3Z, Z is 0. So we have U is T because Y is T. So we have U is T, X is minus T, Y is T, and Z is equal to 0 right here, where T belongs to R. T is any real number. So this is the solution of the system. If we have, so how many solutions we have? So if we substitute T as 1, then we have the value of U as 1, X as minus 1, Y as 1, Z as 0. That is, we have one particular solution. If we substitute T as 2, then we have the another solution, that U is 2, X is minus 2, Y is 2, and Z is 0. So if we substitute T as 3, we have the another solution. So how many solutions we have? We have infinitely many solutions. So this is the general solution. So we can also tally the solution by substituting these values in these equations. We observe that all the equations are satisfied by these X, Y, Z and U. If we substitute X, Y, Z, U in these equations, then all the equations are satisfied by these values. So we can also tally your answer. Next example, solve the equation by any method. So we are given these 2 equations and the unknowns are U, X, Y, Z. So the coefficient matrix is this: 3, 1, 1, 1, and 5, minus 1, 1, minus 1. And the matrix of unknowns is U, X, Y, Z is equal to 0, 0 is the matrix of constant. And then consider the augmented matrix: 3, 1, 1, 1, 5, minus 1, minus 1, 1, and write here 0, 0, A0. Or consider coefficient matrix: and then reduce this matrix to echelon form. This is the echelon form. By reducing this 3 to 1 and then applying all the procedure, we have this is the echelon form of the matrix. So this is the echelon form of the matrix. Then rewrite the equation. And if we observe the number of non-zero, this is always, this system is homogeneous, so it is always consistent. And if we observe the rank of A is 2, rank of AB is also 2, and it is strictly less than number of variables because there are 4 variables. So the equation, the system has infinitely many solutions. So rewrite the system. So we have u minus x minus z is equal to 0, and then y uh, x 1 plus 1 by 4y plus z is equal to 0. And so we have two equations and there are 4 unknowns. So the difference is what? 4 minus 2, that is difference is 2. So we have to assign 2 unknowns. So either assign out of this u, x, y and z, assign any 2 unknown. So we assign y and z. Suppose y is 4s and z is t. So assume z is t and y is s or 4s. In order to avoid the fractions, we assign y as 4s, or just y as s. And then x, from this equation, x is minus 1 by 4y minus z, substitute the y as 4x and z as t. We have this x as minus s minus t. And then equation 1 gives u as minus s. So the solution is what? U is minus s, x is minus s minus t, y is 4s, z is t, right here, where s and t belongs to R, or s and t are any real number. So this is the method to solve the systems by Gauss-Jordan method and Gauss elimination method. So there are 2 methods. So these are some another problems, solved problems by Gauss elimination method and Gauss-Jordan method. So we have the infinitely, in some cases we have the unique solution. In some cases we have infinitely many solutions. But in some cases we have 0 solution. That is, if the system is inconsistent, then system has no solution. And when the system is inconsistent, if the rank of A is not equal to rank of AB, in the case of non-homogeneous system, then system is consistent. For example, solve the system by Gauss elimination method. So this is the system. So reduce the matrix to system to matrix form, and then consider augmented matrix. So this is the augmented matrix: 0, minus 2, 3, 1, then 3, 6, minus 3, minus 2, 6, 6, 3, and 5. And reduce this matrix to echelon form. So this is the echelon form now. Consider reduce the matrix to echelon form. So interchange these first and second row, and then so we have this is the echelon form. And if we observe the rank of A and rank of AB, so rank of A, this is the up to this line. By deleting last column, we have this is the echelon form of the matrix A. And if we observe the echelon form of the matrix A, then there are 2 non-zero rows, and therefore rank of A is 2. But if you observe the whole this matrix, it is an echelon form of the matrix AB. And if you observe the first row non-zero, the second row also non-zero, and the third row is also non-zero, and therefore rank of AB is 3. So in this case, rank of A is 2, rank of AB is 3, and so rank of A is not equal to rank of AB, and therefore the given system is inconsistent. Means given system has no solution. Given system has 0 solution. So if the system, either system, any system has no solution, means 0 solution, or unique solution, or infinitely many solution. So we'll see the remaining problems on these 2 methods in the next lecture.